Everybody. Welcome to yet again another e-learning day. So I'm going to kind of pick up where we left off talking about, well, let me remind you all first what we did last time. Recall if D is a vector space, that has a maximal linearly independent subset, then that maximal linearly independent subset is basis. So I proved this actually last time that if you have a module over a division ring, actually I just talked about fields, but the proof didn't need any of that stuff. If you have a vector space over a division ring, in fact, if you have a maximal linearly independent set, we showed that maximal linearly independent set had to span the entire vector space and is therefore a basis. So it's maximal linear, it's a linearly independent set that actually spans it. Okay, so the first question, like right out of the gate after that, has got to be, okay, how do you know which vector spaces have these maximal linearly independent sets? What happens if they don't? Well, here's the good news. They all do. Here, whatever this number is, every vector space over a field has a maximal linearly independent subset. So has a basis. Let's say every non-zero vector space, because of course the vector space zero has no linearly independent subset. So every non-zero vector space over a field, actually over a division ring, has a maximal linearly independent subset. So it has a basis. And more precisely, in fact, any linearly independent set is contained in a basis of elements. And this was a big theorem that you probably, I'm sure, or at least got thrown at you a bit in linear algebra. You can start with any linearly independent set and you can expand it to a basis, because you look at your linearly independent set. If it spans the vector space, then good for you. And if not, you can actually take that linearly independent set and grow it to a larger one that is a basis. So another way to put this, of course, is that any linearly independent set is contained in a maximal linearly independent set. And this is important even back in linear algebra when you do things like the Graham-Schmidt process, or if I remember that name right. But anyway, so you start with a seed and you build an orthogonal basis, right? And so this one's kind of big. So let's prove this. I'm gonna do something that's more algebra kind of thing, because I'm not gonna assume it's finite. There's easier proofs if you want to be in something like, finite dimensional vector spaces, but why not go for the gusto here? Proof. Let V the non-zero vector space. And X in V a linearly independent set. Of course, I guess the first thing that you might really, if you're hypercritical, say, well, I mean, how do you know there is a linearly independent set? But recall, uh, since V is not zero, it's not zero vector space, there exists a non-zero V in V, and the set V by itself is linearly independent. Because if you have lambda times V equals zero, and you're over a field, I did that actually. Let me finish this off here. Suppose lambda times V is zero. Well, this is a vector space. And suppose lambda not zero. Well, if lambda is not zero, then since we're over a field for division ring, then lambda inverse is this. Therefore, lambda inverse, lambda V, zero, which is 1 times V, which is V. Because remember, this is a unitary module, and this is a contradiction because we assume V is not zero. Therefore, lambda equals 0, and V is linearly independent. So a singleton non-zero vector is a linearly independent set over a vector space. So I can assume this X is not empty. So to take any linearly independent set X, I'm going to take this linearly independent set, I'm going to spread some fertilizer out, I'm going to grow it to a maximal linearly independent set using Zorn's law. So whatever that letter is, the collection of B, where X is contained in B, and B is linearly independent. So what I've got here is I'm looking at this collection gamma, and it's a collection of all linearly independent subsets of B that contain X. So all the linearly independent subsets of B contain X. I always like to start off by assuring myself that I'm not proving something about the empty set, and I will do so this way by noting that X is an element of gamma, so gamma is not empty, because at least it's got X. Okay. Gamma is a partially ordered set under inclusion. This is a big fat set of sets, and take any two of these B's that contain X. Either B1 contains B2, or B2 might contain B1, or might not be able to compare them at all. But anytime you can compare them, they satisfy some rules of partial ordering. And this is just, again, this is just set theoretic inclusion. Now, to apply Zorn's lemma says that if I have a partially ordered set, as I do here, with the property that every chain has an upper bound, and that set has maximal home. Okay, so we need to verify that every chain has an upper bound in the set. Y Zorn need to show every chain in gamma has an upper bound. And let me remind you also, a chain, what does it mean to be a chain? A chain is just, remember, this collection gamma could be apples and oranges, lots of stuff to keep there. A chain is just a subset of this where everything's apples. You can compare it. I'll make that clear when we write this down. So what we need to do is examine the chain and see if we can find an upper bound. So let's let fancy C be a chain. Again. Okay, so this is all these BIs are just stuff that we pulled out of here. And what makes them a chain is if I pick out any two of them, I can compare. J are in my index set here, then BI is contained in BJ, or BJ is contained in BI. One of those two has to happen. So I've got this chain. What's a good idea for an upper bound of the chain? The upper bound of the chain would have to be, or a good choice for that would be a union. Now, again, if I take a union of a couple linearly independent sets, there's no freaking way that I expect the union of, say, two randomly chosen linearly independent sets to still be linearly independent. But chain here is going to save us. So here's what I want to do. I am going to let M be the union of everything in this chain. Just throw it all into a giant M. Okay? Notice that so M is certainly an upper bound for that chain in the sense that every BI is contained in M, right? Because it's the union of all, no problem there. But it's more subtle than that because we need to show that every chain has an upper bound that's in gamma. So we need to show that M is a linearly independent set. Containing X. Right? In other words, we need to show that M actually lives here. It's a linearly independent set that contains X. Now, the fact that it contains X, that's no sweat because every one of these BIs contains X. So M totally contains X. Overkill though. Right? The tricky part is linear independence. So suppose M1, M2, MK is in M, and you have the relation R1 M1 plus R2 M2 plus RK MK is equal to 0. So suppose we've got that relation. Well, of course, what I need to do is I need to show that all the RIs must be 0 because I want to show, my goal here is I want to show that this is a linearly independent set. So whenever I have one of these finite relations, of course, all the RIs should be 0. Now, I don't know much, but I do know that each of these MIs come from M, which is this union. So for all I between 1K, there exists I, I'm going to call this J. For all J between 1K, there exists I sub J in the index set such that MI is in the I sub J. In J. That is to say, M1's in one of these B's, M2 is in another one, and so forth in case of another. Without loss of generality, we can index such that BI1 is contained in BI2 is contained in BI. Okay. Right? It's because any two of these, BI1 and BI2, one of them contains the other. And compared to others, one of them contains the other. So I'm gonna use that to re-index this. So I'm going sequentially to the biggest. So in particular, what this means is that M1, M2, up to MK are elements of B, I, sub K. Therefore, and since BIK is linearly independent, then R1, R2, RK, all the coefficients. So Zorn-Zomer applies. That is, every chain is shown to have an upper bound. And so we can apply Zorn-Zomer. Therefore, gamma has a maximal. So what we've shown is that hence, given any linear subset of B, say X is contained in M, which is maximal linear subset. And M is a basis by the previous because the maximal linear subset vector space is always a basis. And so we've shown the stronger thing that we wanted to show, that is an arbitrary linearly independent set X can be expanded to a basis, right? Let me also note at this point that the expansion, the M, the maximal one, is not unique in general. There's often many ways to do this, which is really, I mean, sort of that's why people do things like Fourier series and so forth and so on. Finding different clever bases that work for your particular problem. Let me also make another, I think, important remark here. A free module of field vectors always has basis. So if you have a free module over a field, not much choice. If your field is Q, right, we've already seen some exotic C modules, right? Things that behave very far from a notion of freeness or basis, right? Over a Q module, there's no choice. If you have a finitely generated module over Q, it's a vector space. It's a finite dimensional vector space. If you have, well, let's take a real vector space. Finite dimensional. It looks like R. Yeah, a little bit. Infinite dimensional might look like this. So it's a countable basis. E1, E2, E3, forever. Where EI is the standard thing where you have one in the ith coordinate, zero elsewhere. But it can be much bigger than this. In fact, here's one just for giggles. Look at this right here. This is like the direct part. This is all the infinite vectors with no restriction. As opposed to the direct sum, there's no restriction here. Now, is this a basis for this? And the answer is no. This is a linearly independent subset of this for sure. But it's not a basis, right? Because, for example, if I have the element in here that's 1, 1, 1, 1, 1 forever, you're never going to be able to write that as a finite linear combination of this. So this is a linearly independent subset of this, but it's not maximal. And if you don't believe the action of choice has ever done anything for you, try to take this subset of this and expand it to the basis, and you will get confounded very fast because you find yourself having to make infinitely many choices pretty quickly, right? It's really bad. Here's another thing. This is obviously an R module where R is the real numbers. So this is isomorphic to, see that or not? This is isomorphic to because again, this structure right here is an R module over the reals, which is a field. So it's vector space, so it's free. This is a direct sum, some number of copies of R. It's not countable. You actually have to have a lot more basis elements to pick this up. This is the direct product as a vector space over R is a direct sum over an index set that's largely countable, right? So, but I take comfort from this because even though this is complicated, I can rewrite this as a direct sum when I think of it as vector space over R, which is kind of cool. Here's another hazard to look out for. This thing right here, as I pointed out, the C1, E2, E3 forever, linearly independent subset of direct product, but it doesn't span it. So you'd have to expand it to a basis. You definitely have to use Zoom's limit. There's another hazard that happens when you leave the nice, comfy realm of fields, and that is you can no longer guarantee that you can expand something to a basis. So Here's a simple example. I discussed this last time, actually. Z is a free Z module. And linearly independent subset. Actually, any number that's not zero is linearly independent, and then if you throw out plus and minus one, any number other than those three for certain purposes here. However, this cannot be expanded to a basis. Can't do it. Because this linearly independent set doesn't span it. So you might say, well, maybe I can make a basis by adding something to it, but any two element set, subset of the integers, it's easy to see. Actually, you should have left some plus any two element subset of the rational numbers is in fact linearly dependent over C. So no chance, right? So really the fact that you can't divide out over Q, this would be no problem, right? Also notice that if you look at 17 in the integers, 17 generates a submodule of Z, right? Z 17, all the multiples of 17 besides Z. Those two modules are isomorphic, but they're not equal, right? The number 17 generates the same thing that the number 1 does over Q. And that's the importance of the field. Let me give you one more example to really annoy you. And yeah, this probably should, in a certain sense, annoy you. Example. I want to consider let F be field. And I am going to let okay, so I want this vector space to be a countable number of copies. Right. So this is a set of vectors alpha 0, alpha 1, alpha 2, alpha n, but it must end in a string sequence, right? So this is just vector space, it's the direct sum. So it has to end infinite string of zeros. This is a vector space over field F, countable infinite dimension. Now I'm going to use this to make a ring. This ring is not, so let me tell you what this ring is. This is the set F from A to D, such that F is a linear function. So this is the set of every linear transformation from B to B. Any of them, right? It could be the identity transformation, or it could be the zero transformation. Anything goes here. And this thing is a ring under pointwise addition. And composition. In a certain sense, this ring is sort of like what you would expect to be the generalization of a matrix ring. If this were just a finite dimensional vector space, then what this would be is just, if this were of dimension n, say, the vector space, and this would just be n random matrices. And the way I combine the functions are just like you do in matrices. You can add matrices, and that's pointwise addition of the function. And you can also multiply matrices, and that's composition function. That's why it's important that to go from B to B. Right? Notice this is ring with one. So of course the identity of this ring is just the function that takes everything in B to itself. Right? Notice that this ring is not commutative. Because compositions of functions, expect to be the finite dimensional analog is probably not commutative matrices. Now, this is a ring with identity as an R module. This giant, for lack of better terminology, this giant sort of matrix ring as an R module. R is free with basis 1R. That's true for any ring of identity, right? It's free. The module over itself, the basis is 1. That spans it because anything in R is R times 1. So therefore, you get to span anything. And it's linearly independent, right? Because if R times 1 is 0, then R equals 0 because 1's got that much power. I will prove so R has a basis of 1 R. And that basis sums. I am going to prove for you that R also has a basis 2 elements. Consider the following two functions. R. So of course these are two elements of R, and here's the way I want them to act. Of course, F and G being in R, they're linear transformations from B to B. So all I got to tell you is what these two animals do to the standard basis, and that completely determines the linear transformation. I did that about 3 models. Let EI equal EI and EI equals 1 to N is basis. So my basis here, I'm taking E1 is just 1 and all zeros, E2 is 0, 1, and then all zeros. E3 is, I wish I had started indexing this at 0. I should have done this speaking 3 and stuff. But anyway, E1 is, this is 1, everything else is zeros. Now, for me to completely determine F and G, all I have to do is explain what F and G do to the basis. Okay, so I'm going to define it thusly. F of EI is going to be E I over 2 I is even. And zero otherwise. So it's going to take E1 to 0, E2 to E1, E3 to 0, E4 to E2, and so on. And I'm going to kind of weave the stitching here. I'm going to do something similar here. E I plus 1 over 2 if I is odd, and 0 else. So this takes all the even bases, E2, E4, and E6, all of these, she takes those to 0. On the other hand, it takes E1 to E1, it takes E3 to E2, E5 to E4, 3, and so I claim that F and G are linear for you. F and G are near. Let me prove this. So suppose there exists RS in R, so these are other homomorphisms, such that RF plus SG is equal to 0 homomorphism. Okay, so let's look at what happens when I evaluate. So we're supposing this happens. Consider RF plus SG E to the 2 Okay, what happens when I take this new homomorphism and I evaluate an EI? Well, the first thing is let's suppose that EI is an E. Well, the first thing I'm going to do is I'm going to plug in EI to G. So I plug EI into this clump and this clump. When I plug EI into G, since I is even, that's 0. So this is RF EI. But actually, let me take one more step here before I do this. This is RF EI plus SG EI. So I want to distinguish what happens here in the even case and the odd case. Okay, what happens if I is even? Well, if I is even, then G is 0, so this it's gone. And this becomes F of EI is EI over 2, right? So, right, so this becomes R of EI over 2 if I is even, right? And on the other hand, if I is odd, this becomes, in this case, if I is odd, then we can ignore the F part, right? Because this bit now that's zero. And this becomes S of, there we go, E I plus 1 over 2. Right. But this is the zero map, right? Because our assumption here is zero map. So this means that this thing acting on any basis element has to be zero, right? So this outcome has to be zero. So in conclusion, so we can conclude that R of E I over 2 is zero for all even i's. Therefore, R of X is zero for all basis elements. Therefore, R is equal to 0. Because as you go through all the even numbers, this is E1, E2, E3, etc., etc. R is 0 on every basis element. It has to be 0 transformation. And you've got something similar here. All R and I. Therefore, SX is 0 for all basis elements. So S is identical to 0. And that shows us that we have linear independence. F E is a linearly independent set. Fantastic. And that's really the heavy lifting because, well, spanning it is actually a little bit trickier thing, but we're going to do it. So let's suppose the trick here is something similar here. I've got an arbitrary element, arbitrary linear transformation here. I want to show that I can write this as a linear combination of f and g. And again, to determine this phi, all I need to do is understand what basis elements. So I'm going to make a couple of definitions. Let pitchfork 1 and pitchfork 2 be in R. And I'm going to define them thusly by telling you what happens on basis elements. Pitchfork 1 EI is phi of E to 2I minus 1. And pitchfork 2 EI is phi of E to the 2I. And I claim I better get this right. Let me make sure I've got this. I claim that phi is that linear combination. I've got my definitions over here, so that's convenient. Let's see what happens here. Consider again Well, I want to beg the question there, do it. I want to consider, I'm gonna measure this by similar just basis sums. So just consider what this does to EI. Well, first of all, this is ball. This is 241 G EI plus Q F EI. So I'm going to break this down by cases. Again, if EI is even, what happens if EI is even? Well, then it's killed. This is killed. This is 0, so it's gone. And this is pitchfork 2 of E to the I over 2. And if EI is odd, this because again, if it's odd, then the F is dead. We only need to consider this, and this should be E to the I over 2. And now, using the definitions of pitchfork 1 and pitchfork 2, this is, let's see, pitchfork 2. What does that do? It doubles the subscript. So this is E of EI. And what does pitchfork 1 do? It doubles the subscript and subtracts 1. So that is this function and phi agree on every basis stuff. So they're the same. So here's what we have, which is probably a little bit disturbing. R is isomorphic to R. No shot there. R is also isomorphic to the direct sum of R with itself. And once you've got this, go by induction, because now one of these R's is 2 copies of R and so forth. And so R is isomorphic to Rn for all n in the natural numbers. So that this free R module that at the beginning was just like one thing actually has a basis of size n for every n. You can take comfort, little soldiers, in the fact that this rarely happens. A ring that resists that. So it's called the invariant basis property. Or the invariant dimension property, maybe. If every free module, if the basis of every free module has the same number of elements in it, right? Any ring that has a division ring as a homomorphic image. So any ring out there, we'll say unitary, any ring that when you quotient out, it's got a division ring, it's a homomorphic image somehow, some way, will have the invariant dimension property. So in particular, any commutative ring with identity, which when you mod out by maximal ideal, you get a field, has this property. So much of what you're going to encounter is going to be no worries. I'm going to finish this off with a theorem that's really more like a blast from the past. You've probably seen this in linear algebra, couched slightly differently. But I challenge you to kind of go through this. It's a good kind of connection with linear algebra and the algebra you're taking now to connect the dots here. Let W, V, the vector spaces. Well, actually, I'm not gonna say it's a subspace. But W, the vector spaces. Over a division ring D over F. You can do a field F division ring if you like. A, if W is contained in V, then W is less than or equal to then D. This is even true if the basis set is infinite. If W is in V, it's a subspace, and yeah, the dimension of W equals the dimension of V, and they're both finite. That's very important here. The W is V. Without that finiteness consideration, it's wildly untrue. C, dim V. This is basically a fancy version of the first isomorphism theorem. D, if F from D to W is a linear transformation, yeah, the dimension of B is equal to the dimension of the kernel plus the dimension of the image. And if V and W are finite dimensional, then the dimension of V plus W is the dimension of the intersection plus the sum. These are probably familiar from linear algebra, but look that up. Okay, you all stay safe, and we will see you most likely by Wednesday.